Alright, so in this video, I am going to talk about the next two tests on that summary of convergence and divergence sheet. So once again, I highly suggest you just have it in front of you and kind of keep referring to it as we go through this. So the next one down the line is called the Leibniz test. The other name for it, and it's actually the more commonly used name, and it's the name that I usually use, is alternating series. So I usually just call this alternating series test. So series that you're going to use this on are ones that are alternating, meaning that the terms go plus, minus, etc. So this -1 to the n minus 1 right there, that makes the terms go plus, minus. And it wouldn't matter if they went negative, plus. That would be fine. It's just that they need to alternate. That's the only thing that's important. So other things that alternate, so it doesn't have to be -2 to the n, it can be -1 to the n. It could be -1 to the n plus anything else, 5. I don't know why I just picked a random number there. And the other thing that's a little bit tricky that does alternate is cosine of n pi. We've talked about cosine of n pi, that it's actually equal to -1 to the n. So that's another one that alternates. And so those are all things that alternate. And from there, this series now, most of what we're going to look at is the stuff that does not include that -1 to the n or the cosine of n. All right, so like the integral test, there are first a few things that need to happen. And for this test, there's actually 3 things that we need to show: decreasing, positive, and a limit going to 0. Maybe I should say 1, 2, 3 there. 1, 2, and 3. So 3 things that we need to show. We want to show that a sub n, so notice this doesn't include the -1 to the n. So you kind of ignore that part and see whether a sub n is decreasing, if it's positive, and if the limit goes to 0. And if all of that is true, then it converges. You're done. All right, so let's look at some examples. Okay, so first example, let's look at the sum from n equals 1 to infinity of -1 to the n divided by 1 plus 2 root n. All right, so the things we need to check for. First of all, is it decreasing? And by it, I mean just the a sub n's, so we ignore the -1 to the n and we look at everything else. So we take 1 over 1 plus 2 root n, and if it's decreasing, then the next term, so when I plug in n plus 1, that would have to be smaller. So now here's my check. The denominator is bigger because I added something. If the denominator is bigger, the entire thing is smaller. So that's true. So it is decreasing. So it's decreasing. Secondly, is it positive? So 1 over 1 plus 2 root n, is that greater than or equal to 0? Yeah. We're adding a 2, adding a 1. There's kind of no question there. It's positive. And then we've got to find a limit. So thirdly, if we take the limit as n goes to infinity of 1 over 1 plus 2 root n, that is equal to 0. We have our 3 things, so this series converges. Sum from n equals 1 to infinity of -1 to the n divided by 1 plus 2 root n converges. And this was by the alternating series test. By alternating series test. Okay. Second example. Let's look at the sum from n equals 1 to infinity of negative 1 to the n, root n, all over 1 plus 2 root n. So there's the two things, decreasing positive. I'm going to jump to the limit part of this because we'd have to show these three different things. And if I look at the limit of everything that's not in the negative 1 to the n, so the root n divided by 1 plus 2 root n, the powers are the same, and that limit is 1/2. And so it's not equal to 0. And so we can't use alternating series. So the reason that I wanted to bring up this example is because it's a very common mistake to see that negative 1 to the n and just assume it converges because it's an alternating series. But that's not necessarily true. All right, so here's what will happen at this point. So the limit of the a sub n, the limit of the stuff without the negative 1 to the n, goes to 1/2, and that is not 0. So this leads to divergence theorem, because if it's not 0, it diverges. But this would mean that the sum of the stuff without the negative 1 to the n diverges. But what about with it? So now let's look at the limit as n approaches infinity of what would happen if we included that negative 1 to the n in there. Because to use divergence test, you have to look at the limit of the entire sequence that you're taking the sum of. So this one, because the powers are the same and we get 1/2, that's fine. But because of the negative 1 to the n, it would oscillate between positive 1/2 and negative 1/2. So this limit actually does not exist, which is still not 0, which still says that it diverges by divergence theorem. Diverges by divergence theorem. So a couple things to note here. Alternating series test only shows convergence. If the limit is not 0, it doesn't mean that that series diverges. So that's kind of one thing to kind of really keep in mind there. So alternating series test only shows convergence. So if the limit doesn't work out, this is most likely a divergence by divergence theorem problem, but you do still need to consider what will happen with the negative 1 to the n in there. All right. The next test down the list is the absolute convergence test. What this one says is that if you take the absolute value of a sequence within the series and that converges, then the entire thing will converge. So let's look at the sum from negative 1 to infinity of negative 1 to the n all over n squared. If we take the absolute value of this one, so if we take the absolute value of it from negative 1 to the n divided by n squared, that really is the series from n equals 1 to infinity of 1 over n squared. P is equal to 2, it's bigger than 1, this converges. It converges because it's a p-series, and because we took the absolute value of it, it not only converges, but we say that it converges absolutely. So this one converges because it's a p-series, and it converges. So it converges converges absolutely. So if we take the absolute value, it converges. So that means that the negative 1 to the n over n squared converges. The other way that we could look at this, so this is sort of another way, I'll do it in a different color here. 1 over n squared is positive. It's decreasing. It's positive. And the limit as n goes to infinity of 1 over n squared is 0. So this one converges by alternating series test. So with the negative 1 to the n in there, it converges. Without it, it still converges. Versus if we look at the sum from 1 to infinity of negative 1 to the n over n. Now, this is one where we could do the same thing with alternating series because 1 over n is decreasing, it's positive, and the limit as n goes to infinity of 1 over n is equal to 0. So this one converges by alternating series. But if you look at this absolute value, if we try to use absolute convergence, if we get the sum, if we take the sum from n equals 1 to infinity of the absolute value of negative 1 to the n over n, that's the sum from n equals 1 to infinity of 1 over n, and in that one, p equals 1, which is not bigger than 1, and so that one diverges. And that's a divergent p-series. So what we call this, the second example, we're going to call this conditionally convergent. I'm going to need a separate paper to explain this a little bit more. All right, so absolutely convergent, it doesn't matter whether we are adding all the terms or whether some of the terms are positive and some of them are negative. Either way, this sum will add to something. Whereas conditionally convergent, if we just add up the terms, we get infinity. But if some of the terms are positive and some of them are negative, we'll actually get a number. So I'm going to kind of expand on this just a little bit more. So we saw that an example of absolutely convergent is the sum from n equals 1 to infinity of negative 1 to the n over n squared. And that's because if we start plugging in numbers, I'm going to expand this series. So the first one's going to be negative because it's 2 and 1. So negative 1 plus, when we plug in 2, we get 1/4 minus 1/9 plus 1/16 minus ... If we added all of these things up, we'd get some number. If we take the sum from n equals 1 to infinity of just 1 over n squared, so if we take 1 plus 1/4 plus 1/9 plus 1/16 and added all those up, we'd get a number. Let me actually undo. The conditionally convergent takes, with an example of this, the sum from n equals 1 to infinity of negative 1 to the n over n. So for this one, that is, let's see, if we start with negative, or if we start with 1, that's negative. So negative 1 plus 1/2 minus 1/3 plus 1/4. If that continued, we'd get a number. And then the weird part of this is that if it's just 1 over n, so if we had 1 plus 1/2 plus 1/3 plus 1/4, and we kept adding there, we'd get infinity. So on this second example, the reason that it's conditionally convergent is it's only convergent because of the pluses and the minuses. There's enough cancellation with the minuses that you get a number. Without that cancellation, it diverges. The sum is infinity. And once again, conditionally, it matters. The negative is important. You get enough cancellation. It is convergent only conditional on the fact that you have those negatives in there. All right, so to check, for absolute versus conditionally convergent, you need to check both the sum of a sub n and the sum of the absolute value of a sub n, and see whether it matters, whether the pluses and the minuses actually matter. Okay, let's do one more example of this. Let's see, where'd that example go? There it is. So let's look at the sum from n equals 1 to infinity of -1 to, let's do -1 to the n all over root n. All right, so on this one, the -1 to the n automatically makes me go to the alternating series test. So I need to check to see, is 1 over n decreasing? So if I plug in n plus 1, is that less? Yes, because the denominator is bigger, so it's decreasing. It's definitely greater than 0. Oops, that's a root n. And the limit, as n goes to infinity, of 1 over root n is equal to 0. Okay, so there's our three things. And so this series itself converges by the alternating series test. So that one does converge. But if we wanted to see, just does it then converge conditionally? So does it converge conditionally? Does it matter whether it had that -1 to the n in there or not? So what we're going to do is look at the absolute value of it. Essentially, it just gets rid of that -1 to the n. So we're going to look at the sum of 1 over root n. So that's a p series where p is 1/2 because of the root. It has a power of 1/2. And if you look at your sheet under p series, it would have to be greater than 1, but it's not. So it diverges. So does it converge conditionally? Yes. It is conditionally convergent. If that -1 to the n was not there, it would diverge. Okay.